Okay. And the other thing I wanted to mention explicitly is the policy about citation. So what you'll notice is that going forward, I mean, I don't like to give too many puzzlesy questions on homework, so there'll be at least 1 or 2 questions where you can probably look up and find answers. So if you do, please cite the sources. Okay, so if we find, we will penalize students if you just take it from some source without actually citing. Okay? And you are supposed to read solutions if you really want to, and then try to answer on your own. Okay, so that's what is expected. And yeah, but it'll only be like 1 or 2 questions, but still, I just want to make the policy clear. Okay, so all right, so that's homework 2. Okay, and it's due next Friday. Okay.
Are we supposed to cite sources where we got definitions and theorems?
Not necessarily. Yeah, unless you actually got some hint about actually solving the solution, you don't need to cite solving the problem. Yeah. So. Okay, so let's continue with dynamic programming. Okay, so last time we introduced dynamic programming, and the way we introduced it is via this example of subset sum. Right. So here the problem was you're given a bunch of non-negative integers, a0 through an minus 1, and you have some target s, and your goal is to find a subset of the AI that adds up to s. Okay, so the sum of the elements in the subset that you picked should be exactly s. Okay, so that's the goal in subset sum. And the way we solve this is first we wrote down a recursive procedure, and this was a natural recursive procedure. Right? We said that we need to find some subset. So a0 is either in that subset or it is not. Okay? And we branched off into 2 recursive calls. Okay, so the first one is if a0 is included, in which case the target sum now changes to s minus a0. And then you had to recurse on the numbers from 1 through n minus 1. Okay, a1 through an minus 1. In the other case, s remains the same, but you still have to recurse from 1 through an minus 1. And we did this, and what we observed is that many examples, the exact same subproblem is solved several times. Okay, and we saw this via an example. And this typically tends to happen if s is small. And we said that at each level of this tree, there were only s plus 1 different problems that you could have. Okay, that was the main intuition. And what he said is that now you can imagine storing the answers, and before you actually make a recursive call, you see if the solution to that subproblem was already solved before. The subproblem was already solved before, and if so, you just look up the answer as opposed to solving it once again. Okay. So this was how. So this is people also call this sort of a thing memoization. And this is one common way to think about dynamic programming. Okay, although I think the subproblems way is, I think, the right one. Okay, and the second example we saw last time, somewhat towards the end, was this example of finding a shortest path in a directed graph. Okay. And the problem there was you're given some directed graph, each edge has some length, okay, which go down on top of the edge. And now your goal is you're given some start vertex and some end vertex. And you are given the number of hops or the number of edges you need to use to get to this, to get from start to the sink. And you need to find the path with that many hops of the smallest total length. So that's the shortest path. Okay, so you want the smallest total length and using exactly L hops. So this was the shortest path problem. And For this also, we had the exact same strategy as we did for subset sum. So we first wrote down a recursive procedure, and the recursive procedure was very simple. So if you want an L hop path going from 1 to V, then you need an L minus 1 hop path going from 1 to some neighbor of V. By a neighbor, I mean some vertex from where there is an edge to V. Okay, so you go from U to W using some L minus 1 length path, and then you take the edge going from that W to V. Okay. And we tried all possible choices of W. And so this is what we did. And then we observed that even here, each time you have only a small number of distinct subproblems. And in this case, we argued that the number of subproblems, that the total number of subproblems in the whole process can only be something like n times L plus 1, or maybe even n times L. So that was what we did last time. And again, you can use the same technique now. So you can say that instead of making the recursive call, first look up to see if you already solved that subproblem. If so, just read off the answer. Otherwise, you make the recursive. Okay, and after the call is done, you store the answer in the corresponding memory. So, did all of you get a chance to think a little bit about this? Yeah, so we did the algorithm last time, but I didn't do formally the full analysis. So I was a little late on putting up the notes. I put them up only last night. So if you guys have more questions on this, just look those up. So the analysis is actually very simple, but it's just that see it written down. Okay. So and it turns out that the running time for this procedure is something like right size of L plus 1 times number of edges. Note that I've always written the memory as n times L plus 1. This is because these are the number of subproblems, right? And we are storing the answers to every possible subproblem. So that's why this is a memory requirement. Turns out that the running time is also quite similar, but it depends on the number of edges. The number of edges could be a little bit larger than the number of vertices, but it's still polynomial. Right, so unlike before, so here, if you remember, we said that the running time here was n times s. We said that this is, strictly speaking, not polynomial in the size of the input, because the input was actually writing down s takes only log s bit, and so this is not really polynomial in the size of the input. But unlike this, here it's actually truly polynomial, because L can be at most n, and you really have, so this is something like n times n. Okay, so m is the number of edges, and n is the number of edges. So this is actually really polynomial. So any questions before we move on? All right. And yeah. Some questions come to you, then you can see them. Okay, so let's look at the common features between these two algorithms. Okay. Now, in both of these cases, there's some sequential decision making going on. Right? So, and this is a common kind of, I mean, when you think of what problems does dynamic programming apply to, so typically it applies to this kind of sequential decision making problems. So why is the first problem some sequential decision making problem? Like you have this set of elements, you have to decide if each of the elements is in the subset or not. Right? So abstractly, you can think of both of these problems as some sequence of decisions to be made. And importantly, there is a reward only in the end. Okay? So, can anyone say how you can think of subset sum in this form? Like it's a sequence of decisions and then you see a reward in the end.
Decisions are use it or use it.
Okay, and what are the rewards? Cognitive computation. No, that's not the reward. I mean, that's the algorithm, right? But in terms of the problem itself, is there? I mean, what do you think of as like? Sorry, somebody.
Finding the subset sum.
Okay. What do you mean? Yeah, did you have this in the? Yeah.
Shortest path?
No. I'm talking about subset sum.
Oh, subset.
Yeah. So what is the reward that you can associate?
Reach the empty set. You have a set that has S and is 0, and you know that.
Well, that's the algorithmically what's going on, right? Like that's the end. But abstractly, what you can think of is, you make some decisions whether to include an element or not. Okay, so maybe you make some decisions like, okay, I will include the first one, I'll not include the second one, the third one, maybe nothing else, and so on. And you get a reward of 1 if the sum of the things that you picked is exactly equal to S. And you get a reward of 0 if the sum does not include, if the sum is not exactly equal to S. Okay. So you can think of this as like a binary reward. Okay. And you're chasing this reward. Right? So in some sense you have a reward that show that, but the important thing is that you know of the reward only in the very end. Okay. After all the decisions are made. And these are intuitively the kind of problems for which dynamic programming works well. Okay. And in the shortest path, the reward is, you can think of it as negative of the length of the path. You like to maximize that. It's like minimizing the length of the path. So again, you know the full reward. You get some partial reward in this process. In the case of shortest path, in this case, you get a reward only in the end. But still, the final value of the reward is only available to you in the very end. Okay? And this is a common theme in problems where we use dynamic programming. Okay? So this is just a meta comment that I wanted to make. Okay? And the reason we're able to solve these problems efficiently, if you think about it, is that there's some resource that's depleting. Okay? Like in the subset sum example, there was this S, the target sum, which was only reducing with time. And for example, if you were allowed, so this is the reason why it was very important to have non-negative integers. Okay, because otherwise maybe you could go very negative and then come back, and then you could have a much harder problem. Okay. But yeah, so actually that's a good exercise for you guys to think. Okay, so if you have subset sum, you're allowed to do negative things, it actually very quickly becomes very difficult. So, alright, and in the case of shortest path, the number of hops was itself some quantity that kept reducing when we did a recursive call. And that was in some sense why the procedure worked out well. Okay. And the other important thing, which is actually probably the most important thing about dynamic programming, is that we are able to abstract out the subproblem in a fairly clean way. Like in the first case, we said that the subproblem is just defined by a small set of numbers, by some pre-specified set of numbers, which are suffixes of the original array. And there was some target. So there was no need to remember all the choices we have made in the past. Okay. So this is some decision making problem, and until here we made some decisions, but the whole state beyond it is just dependent on the subproblem. Okay, so you solve that subproblem optimally, and it doesn't matter what decisions you made here. Okay. So actually there are some interesting cases where that actually matters. So I will try to put that in the next homework. That will be a while later. I forgot about this point. It's actually a very interesting thing to see. So either in the makeup homework or in the next homework. Okay. So actually, how many of you have seen these things called Markov decision processes? Okay, so some of you have seen. So that's one non-standard example, non-standard from an algorithms class perspective of where dynamic programming is. Okay, and that's where you could have situations where what you decided in the past actually matters. So yeah, and in that case, you cannot use dynamic programming. Okay, so you have to do something a little smart. So, all right. Okay, so I wanted to illustrate a couple more. Okay,
So what was the reward in the case of shortest path?
yeah, you can think of the reward as the negative of the total path length. Okay. You always want to maximize reward, let's say. I mean, if you're okay with thinking about minimizing reward, then just think of the path length, and you want to. Yeah.
You said that decisions we make don't affect the decision we make, but it still matters for the final answer what decisions we select along the way, right?
Yes. Yeah, so it matters for the final answer, but you can just abstract it out and say that your final answer is a certain quantity plus this thing, and the certain quantity, it doesn't, how you compute this subproblem does not need to take into account what you've done in the past. And that's the nice thing, that you can just like abstract out what you've done in the past and just focus on what you've done. Yeah.
So how we can make sure that the decision that we are making is the best decision?
So, what do you mean?
So we are following an algorithm, right? So first, we should make sure that whatever that we are proposing is lead to the best algorithm with the least complexity, right? How we can make sure in terms of dynamic programming that it leads to the best, because we can.
You're asking about why is this correct?
Yes.
Right? Okay, so that's a good question. So I actually did not explicitly say last time why this is correct, right? And yeah, so actually then maybe it's worthwhile spending some time on. I wrote it down in the notes, but I think it's worthwhile mentioning in class also. Okay, so I have the slides from last time in my class, but before we go there, so how would you prove correctness for this sort of a procedure? Like what would be intuitively your
Induction.
Yeah, so you do by induction, but there is this weird lookup, right? So if you just had the recursive procedure, okay, so let me bring up the slides from last time. So it's actually very easy to do this, I think. But yeah, let's do okay, let's do this subset sum problem. Okay, so you had a starting index, you had target sum, and if you just had an inductive procedure, recursive procedure, where you just had the black text, okay, not the blue stuff, okay, then you can use induction to prove whatever you want. And now the only thing we are changing is instead of computing the recursive call, we are saying that you compute it if it's not computed so far. Otherwise, you just look up. But now you can argue that anytime you actually stored an answer into your array, it was actually the correct answer. So you can say that for the purposes of analysis, the dynamic program approach, where you actually memorize the answers, is exactly the same as just the pure recursive. And this is how we argue about the correctness of all dynamic programming algorithms. Okay, so we just say that, oh, this recursive procedure returns the right answer by some inductive analysis. And now the fact that you are storing answers and reading them off does not matter, because whenever you stored it, your inductive hypothesis already told you that that was the right answer.
So basically, the lookup doesn't affect
Exactly.
the final result.
Yeah, so for the purposes of analysis, you can pretend that there was no lookup, there was just this recursive procedure, and just analyze that.
You're just shortcutting.
Yeah. So that's a nice point, and this is a common trick for reasoning about the correctness of dynamic programming. Yeah.
So does the dynamic program lead to an algorithm with the least complexity?
No, I mean, so what he's asking is, can you do better? And this is a question that we generally don't know how to answer, right? Like, there could always be a smarter algorithm, right? So it's, yeah.
So for both of the algorithms, you are basically sacrificing your memory to get a better algorithm. So what if the memory reaches to some limits?
Yeah. So this is a great question. So this is exactly what I was going to say, right? So okay, after a little while, I will come to this point. Okay. So memory turns out to be one of like the key bottlenecks in using dynamic programming. Okay. And you can think, are there time memory trade-offs, okay, or running time versus memory trade-offs? And it turns out that for many interesting problems, you actually don't have this. Okay, so there's some very recent results. Actually, there have been results like this, but recently there are very strong results of this kind, that you cannot have trade-offs. So we'll come to that in a little while. Okay, but first I want to give more examples, and I think today we'll see a couple of examples. We won't see this in detail. You will actually work this out in your homework, but I will mention the problem anyway. Okay, and this will be an example where figuring out how to do dynamic programming is itself somewhat not trivial. So, and I wanted to say that is sometimes normal. Okay, like it may not strike you at first glance that this is a dynamic program. Okay. I'm sure all of you faced this if you guys did interviews, right? Like it's one of these common interview questions. So, all right. So that's that. So let's start with a very simple question. Okay. This is an example of why dynamic programming often is used in like control theory type problems, where you have to make some decisions one after the other. Okay, and the problem is the following: you're given a bunch of pieces of k. Okay, so you have k pieces of k on a certain day. Okay, and so the rules of the game are as follows. Okay, so on day 1, you are presented with k pieces of k. Okay. And you can either eat all the pieces, or you can eat a few and save the rest for the next day. Okay. So okay, so you eat, let's say, some n1 pieces on the first day, and you save the rest for the next day. And here now you have k minus n1 pieces left, and here you eat some n2, and so on. So now, what is the satisfaction you get? So I define it as follows. This is just a modeling. Okay, so this is there are probably many ways to model it. But I'd like to say that okay, so if you eat a lot of pieces, there's some diminishing returns that kicks in, right? So if you eat everything on one day, then probably some diminishing function of n1. So a common thing that people use is this function of log of 1 plus n1. Okay. So log, note that it looks like this. It looks like it still grows, but grows slower and slower as you go higher. Okay. So this sort of a thing is reasonable for help. Okay, but the point is that it could actually be any function. And the nice thing about dynamic programming is that it allows you to solve it for any function. But let's say it's the log, if you keep it simple. And the next day you get something else, and so on. But you've already stored the cake for a while, so presumably you won't get the optimal enjoyment after a certain time. Right? So assume that there's some decay factor beta per day. So here you get beta times log of 1 plus n2. The next day you get beta squared times log of 1 plus n3, and so on. And beta is some factor, it depends on how well you can preserve cakes. Right? So it's, let's say it is something like 0.8. So it's some factor smaller than 1. And now the question is, how do you now, given some k and given the value of beta, how much do you eat on each day so that your total satisfaction is as large as possible? Okay, so this is question here. And again, this should remind you that there is some sequential decision making and there's some reward that depends on all the choices you've made. Right. Yeah.
So I guess you could just calculate, and you could make hand calculations for each like log of like 1 plus ni, and then you could iterate through like each day, like supposing you use like you ate 1 piece a day the first day, you could just look up that sum, and then let's say you added 2 the second day.
Right. So that's roughly the idea. Anyway, this is a homework problem, so you will figure out more details afterwards. Okay. So, but yeah, so that's the rough idea, right? Like first come up with a recursive algorithm. Okay. And then see what subproblems are being solved, and you try to remember the answers. So this is a very simple problem for which there's a clean dynamic program. And it doesn't even matter what this function is. It could have been a much more complicated function. Maybe after a while the reward goes down. So you can model. Point is that you can model basically anything by doing this. All right. So again, this is just a okay. So there's a couple of other examples that canonically you find in textbooks on dynamic programming. I thought I would at least mention these because they are, somewhat. I want you to see this. So in some of them, there is the notion of sequential decision making is very explicit. Some of them, it's you just view it as a memorization trick. Okay. So yeah.
Can you go back a slide? I think I missed it. What is the constraining factor for eating the whole cake in the first day?
Sorry?
What is the constraining factor for not eating the whole cake in the first day?
There's no constraining factor. You can eat it if you want. It's just that your reward, is total satisfaction is probably higher if you wait. Okay. So yeah, no, I mean it's log of 1 plus k, right? So that's the reward you'll get if you eat everything on the first day. Okay. So but it's just that if you see the plot of the log, doing 2k by 2 will probably be better if your k is somewhat big. All right. So here are a few other examples. You will find many of these in textbooks. So I just thought I'd list some things. So the first one is the recurrence for the Fibonacci sequence. Right. So hopefully all of you have seen this. And if you just write a recursive program where you try to, so you just say, okay, define this function flip of n, and you just say return flip of n minus 1 plus flip of n minus 2. If you just execute it, what is your guess? Would it, how long would it run?
Exponential, isn't it?
Yeah, so it ends up being exponential in n, just because you make two function calls, one with n minus 1, one with n minus 2, and this recurrence solves out to something very big. But of course, this is the canonical example where you can actually remember the values and benefit, right? And in fact, in this example, you don't even need to remember all the past. So this is one example, going back to his question, where you don't need too much memory, where you realize that, oh, okay, to compute n, I only need these two. So if I start building up from the first value, then you only need to store two of these things, in principle. So that's the sort of, so this is one canonical example. And another example that you often see, and this is something that LaTeX always does, okay, is how many words to put on each line. So if you put too many words in one line and the next, because you want your paragraphs to be all to be aligned on both the left and the right side. So it needs to look good. Okay. So if you put too many words out here, then maybe you'll just have some largish. Maybe if the words on the next line are all somewhat long, you see Word often does a pretty bad job of it, or used to in the past. Okay, so and you see like these big lines with like lots of spaces in the middle, sometimes spaces in the text and so on. Right? So yeah, so it's actually a non-standard problem how you decide what to put on each line. And turns out that you can have some kind of a mental model for how aesthetically pleasing it is. And the one that LaTeX uses is something like the number of spaces you have on that line squared. That's like the penalty. Okay, and you want like the total penalty to be somewhat small. Okay. Becomes very similar to this cake eating type question, turns out. Okay. But you have to figure out basically how many words you have to put on each line. Okay. And you get a reward at the very end, which is like the total penalty. So yeah, so this is one standard example. Okay. Another question is, there are a lot of string problems that basically reduce to dynamic programming. Okay. And a canonical problem is this question called longest common subsequence. You're given two strings, let's say A1, A2, A3, some AN, and G1, EM, and you'd like to find a subsequence. So these are two sequences of characters. Right? A string is basically a sequence of characters. Now you would like to find subsequences that are equal. Okay, what does that mean? So you pick a subsequence like this, perhaps, and you find some subsequence of this one, such that if you only looked at these subsequences, they should be equal. Okay. And now the goal is to find the longest such subsequence. Okay. And these kind of problems are used in things like genome alignment and so on. Okay. So actually, yeah, after this human genome project started, I think there's been a lot of interest in studying dynamic programming algorithms. There's a lot of string problems reduced to dynamic programming, and a lot of pattern matching type methods become faster. Okay, so that is one big area in itself. So that's one. And also, as I said, dynamic programming originated in a very control theory type setting. So if you go to the course web page, you'll find some historical notes on dynamic programming. Okay, so like interview with Bellman, who first came up with the name and so on. So see the course. Okay, so these are just some examples. Okay, so, and right, so what are the issues with dynamic programming before we go to our final example? So one main thing is defining the right subproblems. And how you define subproblems could sometimes actually determine how much memory you use, how much, what the complexity is, and so on. Okay, so that's one common issue that you will face. And hopefully, yeah, so homework 2 and homework 3, you'll see some examples where you will have to define subproblems the right way. All right. And the other thing that you should, the other main issue with dynamic programming is the memory usage, as he was mentioning. Right? So like in the first example, we said that you use for subset sum. Use n times s space. And if s is fairly big, then this could actually be really bad. And in general, there is no good way to actually, this is of particular concern because very often we are okay with time being somewhat large, but we are not okay with space requirements being too large because RAM is usually not that big. It's growing, but it's not huge, right? So this turns out to be a common issue, okay? And so that's why this is a very active area of research. So for problems like common subsequences and so on, which are actually used a lot in practice, people have found ways of reducing the memory by coming up with some approximate solutions. Okay. But for problems like subset sum, turns out that there are some strong lower bounds. Okay, like there are actually, even if you want to just, yeah, here approximation doesn't make sense, but yeah, so here there are some strong lower bounds for how you solve it. And people have studied these like time-space trade-offs in this context. So, for instance, some result that says if you want to use some n times s to the half space, then you can't do any better than some 2 to the n power half or something like that. Okay, so some non-trivial things like this are possible, but not in general. So that's yeah. So in fact, we'll see some example of this soon. Right, so that's one comment about memory usage. The other way to think about dynamic programming is that it's basically recursion but done correctly, right? Like you're not recomputing answers that you've already computed. Okay, so this is like the memorization view of dynamic programming. Okay. So these are some common things to keep in mind for dynamic programming. Right, so then let's go to one example, which I think is a non-trivial example of dynamic programming. So this will be one thing that you see. So, and this is called the traveling salesman problem. So how many of you have seen this problem before? Okay, most of you have seen the problem. So let's define it anyway, just for the purpose of being on the same page. Okay, so the problem is the following. So back in the day, people used to go from city to city or place to place trying to sell goods, right? So that's the context for this problem. Okay, so you suppose you have n cities. Let's call them let's label them just 1 through n. And the distance between city I and city j is given by dij. Okay, so you're given this matrix of distances between pairwise cities. And now the salesman starts at city 1, okay, which is his home city. So let's say it starts off somewhere. Yeah, it's close enough to Salt Lake. Okay, so start off city 1, okay, and then you go wherever you want. But the goal is you need to travel to each city exactly once and then come back home. Okay, and you would like to minimize the total distance traveled. Okay, so if this is 1, this is 2, this is 3, 4, 5. You can do something like 1, 5, 4, 3, 2, 1. That's a valid solution. But if you prefer, you might be able to do 1, 2, 4, 3, 5, 1, something like that. Okay, so you have to go to everybody exactly once and then come back to your starting point. Okay, so that's the goal. And you would like to minimize the total distance that is traveled. Right? So is the problem phrasing here? Okay, so what is a naive solution to this? Yep.
You can like try each sequence and then like compare and get the minimum one.
Right. So the naive thing is just for every permutation of 1 through n. So you have to visit every sequence exactly, every city exactly once. So the order in which you visit the cities is the only thing that matters. So for each permutation, of 1 through n, compute the total length to travel in that order. For each permutation, let's give some name to the permutation. Let's call it P1, P2, Pn. P1 is always 1. You start with. Okay. So look at permutations that start with 1. And what did you like? So what does this mean? So you look at P, P1, P2 plus P, P2, P3, so on, plus P, Pn, P1. Okay, because you have to come back to P1. Okay. And so that's the order in which you're going to travel, and you find a P that minimizes this one. Okay, and you run over all permutations. So how long does this take? Okay, so this takes roughly n factorial time because there are n factorial permutations. You have to be very precise, it's n minus 1 factorial. But then you have to compute this thing which takes time. Okay, so it's roughly n factorial. So naive solution has but it's pretty nice with space, right? So the space is only n squared, which is, I mean, it's even if you think of the extra space you use, it's only constant, or maybe n, because you store the permutation. Hence, I wrote n squared because dij's there are n squared. Right? So the space is something like that, and time is this. So now the question is, can you do better? Can you come up with some recursive formulation for this problem? Okay. So we have plenty of time, so I'm going to actually do this slowly. Right, so how do you come up with a natural recursive formulation for this problem? Okay. So this is one naturalish problem for which it's not clear that you can use dynamic programming and come up with a clean recursive formulation. At least I think. Yeah.
So we can come up with this scenario that you start traveling, and for example from point 1 and then back to the point 1 again. So what happens is that in each step we have to compute the distance regarding to starting point. So we have distance, for example, from I to 1 plus the cost of computing the I by itself.
Cost of going to I.
Yes. So we have two terms, right? First, whatever that we travel and whatever we are going to travel. So it's going to stand I plus 1 plus cost of I.
But so what does cost of I mean?
So I mean that because in each point we have to again make a decision, right? So this cost I also can be divided into some recursive problems. So now let's suppose that at this point I is going to be like 1. So again it could be, for example, the cost G plus G and I if we go from I to G plus cost of G, and so on and so forth.
So that might be fine, but how do you ensure that you visit every city exactly once? So you're basically saying, okay, I mean, what you seem to suggest is some kind of a shortest path type recurrence.
Yes.
So you're suggesting that, okay, to go from I have to go to a certain point, so then I, try to go via a certain intermediary or something like that. So that's fine, right? But the main difficulty in this problem is not going to some particular one. It's the fact that you have to have one tour that visits everyone and then comes back, right? So there is this important thing that you have to visit everyone. So you cannot let go, you cannot not remember that fact, right? Like you can't just say that, oh, okay, I'm going to try going to this vertex. And trying to go to like vertex 1 first, vertex 2 first, vertex 3 first, and so on will clearly not work, right? So it's so you have to somehow make sure that all of them are covered.
But in every decision we can exclude whatever that we visited, right? And
Right, but how do you choose which target to go to next? So you could say that, okay, I don't remember who, what I visited. I don't try to go to stuff I visited in the past. You still have to make a choice about where to go. Right, so anybody else? Yeah.
You always pick the shortest distance from the village you're at to unvisited them.
So that's a good greedy strategy, right? So what she's suggesting is, at every step, try to go to some node that you've not visited and try to go to the closest such node. So this is a greedy strategy, but you can easily come up with examples where this leads to some suboptimal tours. Okay? Like, I don't know if I can come up with one off the top of my head, but so let me add a new slide and just note it down as a possible idea. So candidate 1. So visit closest time. And you can imagine this sort of a thing failing if, actually let me not spoil this diagram. So here it seems clear that following this strategy will work, right? But now imagine trying to do something where I force you to But so it is possible to come up with things. I don't know if I can come up with one off the top of my head. Okay, so but this is a well-studied thing, and it's not optimal. That's how it works. Indeed. Suboptimal tours, and in fact, there's a lot of study about what it does if you have like two-dimensional points, and there you can show that it has some 3/2 approximation or something like that. Okay. But it's not optimal. Yeah.
How does that make sure that we visited every node? If we visit closest unvisited node,
Right.
how can you?
Right. Maybe no. But you always visit some unvisited node, and in the end, if there's nothing unvisited, you go back to the start. So actually, maybe that's one way of getting a counterexample, where maybe you ended up with somebody who's too far away, and might be one way of getting a contradiction. Okay, like you might have something where you have stuff like this. Sorry, something like this guy, where this length is slightly less than this length. So L1, L2, and L2 is a little bit larger than L1, then you will end up doing some zigzagging of something like this, and then you'll end up at some point, and now you're very far away. You may have been better off going like that. So that could be one example of a pattern. Yeah. Although I'm not 100% sure if this works. so it's hard to come up with counterexamples. I will probably include one in the lecture notes, but it will take me some playing around to come up with it. Yeah. Yeah. So this is a good start. I mean, it's natural strategy, and it turns out to give some small constant factor approximation on the plane, okay, but not in general. So. All right. So what other? Yeah. So anything else? Come up with? Yeah.
So you can just do the traditional way, just go through everyone, and recursively, you have another array to store all the indexes. If you go to this one, then you eliminate the first index, and then recursively go to the next. But you will go everything. So in order to optimize that, you can also introduce another value, saying that for the first one, you added all the values together for the whole path, and then you look it up for the next recursive step to say, oh, you go through 1 and 2, that is bigger than the first one, then you don't go through that, and then you keep going in the next one until you find something that is less than the first step, and then you update that.
But you are still going from 1 to 2, right? How are you making sure that you visit everybody?
So for each recursive, then you can go through from the index from 1 to n.
And you're going in order.
Yeah, you can do it in order.
So I think what he's trying to suggest is build a tour that initially goes from, let's say, 1 to 2 and back, and then let's say you want a tour that includes vertices 1, 2, and 3. Are you trying to say, let's try to see where 3 can fit in into that tour? Is that some way of
after you go to 2, there's only 5 or 3 left. So
Okay.
next time you go either 3 or 4 or 5.
Okay.
You also do every scenario.
So you go through, all of them, but and then you keep track of which set you have not visited.
Yeah.
Okay, so I think that's roughly what I was also trying to get at. Okay, so sometimes what he's saying is, at each step, try to remember the set of vertices that you've not visited so far. That's something you throw into the recursive call. And then what other information do we need? right? So if you had to come up with a recursive formulation. So actually, before we get there, one thing to note is that this is in some sense cheating, but you should be thinking about things like this when you are coming up with algorithms, that you can never hope to find a polynomial time algorithm for this problem, because this turns out to be NP hard. So in some sense, a greedy algorithm which runs in polynomial time is, you don't hope that it's always correct, okay? Because the problem is actually NP hard, and if you come up with a polynomial time algorithm, you have done something very marvelous, which you don't, which you don't expect to do, right? So that's the reason. The best you can hope for is probably something that's exponential. And what we've come up with is an algorithm that's actually something like 2 to the n running time, but note that 2 to the n is still significantly better than n factorial, because n factorial is almost like n to the power. Alright, so with that being said, let's try to go to what he's saying. So, and somehow the key idea is that now the subproblem must be the set of unvisited words. Okay, so you must somehow remember the set of unvisited vertices, and that should somehow be a parameter to your subproblem. And that's what he's saying, right? And so that's fine. So that's something you've got to keep in mind. And do we need anything else to define a subproblem? Right, because we are starting at 1. Yeah.
We have to keep track of the original node, because at the end of our recursive calls, we have to return back to the original one.
Right. So that's another important thing, right? So this is one key idea. So the next important thing is that must remember the start, which is, in this case, that is easy. It's always the vertex 1, right? You're given that thing, so you know you have to get back to that thing. Okay. But yeah.
Also the node that our current node.
Right. So you have to remember where you're at. Okay. So because that's where you're currently starting, right? So remember, this is what I was trying to explain earlier when I said that your subproblem must abstract out all the decisions you've made in the past. Okay? So if you knew your past, you know where you are at currently. But your subproblem should also encode that information, because you should be able to solve your subproblem independent of what you've done in the past. Okay? So let's define also, throw that also into the subproblem. Just say that, where are we at? So these are 3 things that all need to be somehow encoded in the subproblem. Okay, if you need to be able to solve it independently of the whole thing, then you need to have all of these. Now the question is, are these enough? Okay. So what I seem to be suggesting is that you need this set of unvisited vertices. Let's call them S. Initially, it's the whole set. And you must remember the start, but you don't need to remember it, because in our problem we are given that that's equal to 1. Okay. So that's that. And you need to remember this vertex U, which is the vertex you are currently at. Okay. Now, can you write a recursive formulation that only involves these guys, or do you have to have more?
Well, you also need to know what you visited.
Yes, but if you knew the unvisited vertices,
Oh,
you can
that's
figure out.
Yeah.
Yeah.
True.
Because we're trying to minimize how far we go, it seems like we also need to keep track of how far we've gone.
the
So
distance.
somehow the order of the choices we made in the past matter.
So does the order matter, or is it just the cost?
The total cost, which is in that, if we knew the order of what we had done, that would also be sufficient, but just the total cost, right?
Right, so that is definitely true, right? So you have to remember what the total cost is, but do you actually need to, what is the total cost? Yeah. It's a good point, but do you actually need to remember it as a, pass it as a parameter to the subproblem? Because
Sum it up on the way back out.
yeah, so we'll see that you don't really need to store it, but let's write it down because it's an important thing to keep in mind. Okay. Yeah. So I saw another hand. Okay. All right. Okay. So good. So now let's come up with a recursive formulation. Okay, where you have all of these parameters in your subproblem. So let me write out in words what the subproblem is. Okay, so the subproblem in words. So sometimes this helps. Okay, so you will find is starting at U. Okay. Visit all the vertices in S, precisely once, then go to 1. So this is the goal of this subproblem, right? Like you, starting at U, visit all the vertices in S exactly once, then go to 1, and in the process minimize the total cost. So this is how I would like to phrase the subproblem. Let's think if you can use this to come up with a recursion. Yeah.
Remember the start.
Yeah, so you don't have to remember it. I didn't actually use it in the, as I was saying, in general you may, I mean sometimes you might have to, but in our problem we are given that the start is always 1. So you don't have to remember. You only, so for in this formulation I have only used U and S. Okay. I have also not used this cost, hoping that it will somehow show up naturally in the recursive procedure. But these two you definitely need to keep track of things that you visited, things that where you are. Because where you are is somehow a function of the history, and we don't know. Alright, so given this, can we come up with a procedure? Let's call it PSP sum, which is like the subproblem of which is defined by U and S. So let's say I have a procedure that does this. Okay, so this is a TSP subproblem that takes in a U, takes in an S, and gives the best solution, which starts at U, visits everybody in S, and then goes back to 1. Yeah.
Sounds like a shortest path problem.
But the important thing is that
hitting each node.
yes. So in shortest path, you don't care who you hit.
Right, but in this, it's the shortest path, but you have
to
hit every member in the set.
In the set S. Yeah. And that's the crucial difference. Yeah. Yeah. So I guess yeah.
Would you recursively, so one recursive call would be to solve from, you're starting in U, so you have S the set that you haven't visited?
Mm-hmm.
Okay. So one recursive problem would be to solve from like you and then using the set of stuff that you haven't visited, and the other problem is the set of stuff you have visited back to 1.
So why do you say, well, so the first part I agree with. What is the second part? So why do you have to go back to the set that you have visited?
Oh, I guess not that you have visited. I guess it would be still be the unvisited set, but back to 1.
Okay.
Or I don't know. Because you need a way to get back to 1.
Right. So that's something, yeah.
So we can write this one equals to here we saw v and s minus u,
Mm-hmm.
and v shouldn't be equal to u, and it shouldn't also be equal to starting
Okay. One. Yeah.
So it can be there.
Can it be outside of S?
No, it also
Also has
should
to be.
belongs to S. So it should be minimum of this plus distance of v to u.
So yeah, so that's, I will write that in a minute. Did you have a similar solution?
Yeah, just framing it as a for loop, you want to compute for every vertex in S.
Yeah.
Distance from U to V, and then the subproblem would be V S minus V.
Yeah. So that's the natural way to frame it. Once you've defined the subroutine, right? So once you define the subroutine, so how would you implement it? So ESP sub of U is for all V in S. You do the following: compute let me just write val equals this, which is distance from U to V. We call this DUV in the past, but I'm just calling it this here, plus ESP sub. And you want to call the subroutine, right? So what both these answers are trying to do is basically from you decide what is the first vertex that you visit next. Okay, you have to visit everybody in S, right? So the next vertex you visit has to be somebody in S. Okay, so you try all possible choices. You say that okay, the next vertex I visit will be V. Okay, and if it is a certain V, then you pay a cost of this dist of uv. And now what is the subproblem that you have left? So now you are currently at V, and you need to visit everyone in S except V, because this is the first one you've visited so far. Everybody in S is remaining. So you need to visit V and S minus V. And what happens to the going back to 1? The point is that the subroutine takes care of it, right? The way I have defined the subroutine is starting at U, visit everybody in the set S that you prescribe exactly once, and then go back to 1. Okay, so you are forcibly including that cost in the final. Okay, so that's why you don't have to really bother about this. So for every V in S, compute this value and return the smallest of the So this is again informal. This is formally you have to keep track of some variable, and if it's smaller than that, you update that variable. Okay, so I assume all of you are programmers. You know how to do this. Yeah.
In the for loop, it says for all V and S, you want to intersect S with the adjacency list of U.
So currently I'm assuming that you can go from any vertex to any other. If that were not the case, you will have to do it. So currently I'm assuming that, remember the problem, the way I set up the problem, you can actually go from any I to any to j with the cost of di. Right? So what he's saying is if you just had a communication graph, right? Like if you can only go from U to a small set of lines, then you'll have to also intersect it with the neighborhood of U. Okay, so that is correct, but in our case, we are assuming you can go from anywhere to anywhere else. Yeah, so that's good.
But we have to mention that V is not equal to U and V is not equal to starting point.
Oh, right. I forgot about your comment, right? But note that U is not in S, right? So you don't really have to mention this. Okay, U is your starting point. S is a set of guys you need to visit. So implicitly, you have that U is not in S, because next time when you call the subroutine, you're calling it with S minus V, right? So you've removed V from that. So your set will never contain that U that you start with. There is a base case in this case, which is a little bit important. Okay, so what is the base case? Yeah, actually, what is the base case? Yeah.
As is empty, you add that to the one.
Right. So the fact that you need to go back means that if S is empty, then you are at the starting point U and you need to go back to 1. Okay, so you have to return. Yeah, so if S is empty, you return distance from U to 1. And this is how we are capturing the return to start. Okay, so the base case is where this thing comes in. Okay, so that's the so this is the procedure, right? And right, so this, as I mentioned before, is not terribly efficient, but you can try to analyze how long it takes, right? So there are all these recursive calls, and then you're visiting. So each subproblem is now defined by a vertex and a set. Okay. So how many subproblems are there? Okay, so yeah, so why is so those who said yeah, so subproblem is defined by U and S, right? So U is the start vertex or the current vertex. Okay. So how many subproblems are? But why did you say n minus 1 factorial?
Because we are not we are starting from the first vertex and we have n minus 1 vertices to visit. So in each recursive call, we will have one less vertex to visit. So in the
so that's true if you just did this without thinking of how many subproblems are there, right? So you're giving me an analysis of this procedure, a running time analysis of this procedure, and that is perfectly correct, right? So what he's saying is, initially S would be so initially, right? So U would be 1. This would be U would be 1, and S would be 2 through n minus 1. 2 through n. So this would be the initial thing, and you try n minus 1 possible things, and then next step you try n minus 2, and so on. But so that's the running time of this recursive procedure. But that's not what I'm asking. Right? I'm asking you how many subproblems are there, okay, which is we are hoping that there are repetitions, right? That's the whole goal. So we already said that the subproblem is defined by one U and a subset of vertices S. So how many U's are there and how many subsets of vertices are there? So yeah, the first part is easy. So there are n candidates for U at most. Like one is for yeah. So the number of candidates for U is exactly n. And what is the number of candidates for S?
N minus 1.
How many?
N minus 1.
But it's a set, right?
Right.
So how many? I know that the number of elements in the
N
set.
minus 1 factorial.
So how many? The question is how many subsets are there for an n minus 1 sized set, right? So if I take the set 2 through n minus 1, and I would like subsets of it, right? So you'll get some subset of it. The point is that there are not n factorial or n minus 1 factorial subsets of a given set. There are only 2 to the power of n minus 1 subsets, because each one could be either included or not. So these are just subsets of 2, 3 of n minus 1 up to n. And so the number of them, this is equal to 2 to the n. Okay. And right, so the number of candidates for us are just subsets of these things, which is exactly 2 to the n minus 1. And in principle, not all of them may be false, but in this case, all of them could potentially. So this is exactly the number of subproblems. That's n times. And this in general is way less than n minus 1 factorial. So you can hope that there's a lot of reuse in this process. So you can just, yeah, so you can see the number of distinct subproblems is only that. And so you can do exactly the same thing, right? So you can store answers to all these subproblems. But actually, if somebody tries to implement this, this will be a bit of a mess because you have to store all the subsets and you have to have a nice data structure to store all the subsets. Yeah, but you can do this in principle. So, right? So and here again, so the final algorithm is, instead of doing this, we do the usual trick. Instead of making the recursive call, so you possibly look up, and if you don't find it, then you make the recursive. And this process, you can see, will take the total running time will turn out to be something like O of n squared times 2. So that's what it is. I thought I had a lot of time. It looks like I have reached the end. Right? So yeah. So see you guys next time.